So today I'll be presenting research from Peter Thoman and me from Innsbruck University, and also Luigi from Salerno. We've been for the last couple of months working on a new SYCL implementation called SimSYCL that's radically different from any other one that's out there so far. And I'm happy to show it to you as the kind of the first audience. So why a new SYCL implementation? What are we trying to do, and why do we have to start all over again? The use case or the target for SYCL implementations is typically, well, running programs fast on a GPU or FPGA or any other accelerator hardware. And like as we've seen in the last couple of talks, trying to remove obstacles in the way of performance, squeezing out some latencies here, getting better resource usage there. And but what the typical performance optimizations that a SYCL implementation has to do is at odds with is, well, the developer experience at some point. Because like what you might have on a host program, things like bounce checking or assertions you typically don't want to have in your fast path of a SYCL implementation, of a SYCL program, or of another GPU program, because, well, it costs you performance. So one thing we want to have in the SYCL ecosystem is an implementation that easily quickly tells you about errors you might have in your code, about misconceptions you have about how to use certain APIs. And then there's another thing that we actually encountered in real life, and that's about portability and simulation. So there's two use cases. One is we in my group, we also work on Celerity. You might have heard about it. It's a distributed memory API that's very close to SYCL, but runs on multiple nodes or multiple GPUs. And for this, we have, for example, we have code that needs to perform complex device selection. So we want to pick on any system the optimal set of devices, the optimal set of GPUs, for example, to run a program on. And now we have this code and we want to unit test it. So how do we unit test code that performs subset selection of devices on a system? Well, we just have a couple of machines. We have a machine that has a couple of Intel GPUs, a machine with a couple of NVIDIA machines, GPUs, one machine with both, just to run unit tests. So that's not, I mean, that works, but that's not very economical. So we kind of want to be able to mock the behavior of SYCL in a way that we can unit test our code. And another thing that we were running into was portability. So imagine you have a program that you just ported from CUDA to SYCL, and you want to, and it works. So you got the correct results, and now you want to run the same thing on an AMD GPU, and suddenly you get garbage results, and you want to know why. So one reason might be difference in hardware, because you might have different subgroup sizes, different default subgroup sizes, for example. And so you kind of want to be able to verify that a program that you have runs on different types of hardware before actually deploying it to a real system or to a real set of GPUs. So, and there's now other things that we encountered, like in the SYCL specification, there's a ton of requirements that's placed upon the caller of certain APIs. There's usually written in prose. For example, like if you enter a group barrier from one work item, you have to enter the same group barrier from all work items within the group. And this is a requirement that's not easily asserted. That might be able to be detected from a specialized compiler, but it's not it's not trivial to do so. And so we want to be able to kind of enforce this, have an assertion-like functionality that tells us when we misuse an API. And yeah, also like in general, debugging a SYCL application especially when it comes to kernel functions, is difficult, you can rely on platform or backend tools like CUDA-GDB, for example, or Compute Sanitizer in order to detect some errors, but it's typically not as simple as just single stepping through functions. So what we want to have is a SYCL implementation that's really fully developer focused. So we can sacrifice performance almost everywhere as long as it benefits the developer in a sense that they can arrive at the correct or portable product faster. So just to show on where we want to see SimSYCL in the broader SYCL ecosystem, SimSYCL will be a great tool for developing SYCL applications in that it's pretty easy to set up on your local machine. Compiling is fast. You can easily debug. You can easily debug your programs with SimSYCL and make sure that it will then also be portable to any other SYCL implementation because it's strict about adhering to the standard when it comes to interfaces. And then in the next stage where you're doing things like continuous testing or you're doing verification in your CI pipeline, you want to be able to simulate different platforms, simulate different devices in order to make sure that whatever change you just made is actually portable to all the hardware that your program is intended to support at some point. And then, you obviously also want to test against other SYCL implementations to see if performance is any good. And then in production, you use one of the SYCL implementations that actually targets your accelerators like adaptive CPP and TPC++ in order to get the performance that you want from SYCL. So in order to get to this debugger friendliness, we kind of we implement the API in a way that's correct, and in the sense that technically correct is the best kind of correct. As it turns out, SYCL has at its core DAG-based asynchronous execution, but there's almost no part in the spec that actually requires us to do asynchronous execution. So if you take a look at the program on the left, we perform a couple of memory operations and kernel launches, and the execution graph, the DAG that results from this, you can see in the middle, which basically tells us that the copy and set operations can run in parallel, and also the kernels can be launched in parallel, A through C, and then kernel D depends on the rest. So we can do either concurrency, task parallelism between these kernels, or we can execute them sequentially, and that's up to the SYCL implementation. And now what SimSYCL does in this case, it simply executes every SYCL operation from top to bottom. And as it turns out, since you can always, through SYCL events and accessor dependencies, you can only always create dependencies upwards and never downwards in the order you write the code. You can simply just execute from start to end and never introduce any kind of deadlock with that. So that's what we do. We simply execute all the SYCL operations top to bottom, which makes it easy to step into and have a consistent execution schedule, kind of. And it turns out this works almost always. Like I said before, there's a couple of very weird edge cases that I hope that very few programs actually use, and that one of them is if you use a SYCL host accessor. So this is not an accessor within the host task, but like an accessor within the application main thread. And then you launch a kernel that uses the same buffer with an accessor from a kernel. Then the kernel has to wait for that accessor to go out of scope. This is something that doesn't work with the synchronous execution. And another thing is that you can, in principle, communicate between your application thread and a running kernel, or your application thread and a running host task through shared memory atomics, for example, or just generally through C++ concurrency synchronization primitives. also something we can do, but which we assume is pretty rare. So now let me stay at this slide for a second. So what we do now here in order to execute kernels is also that we simply turn that parallel for that you write in SYCL into a sequential for. So for a simple parallel for kernel, that's pretty trivial. You just iterate over the entire range and execute the kernel function for every item. No surprises there. It becomes more interesting when we look at ND range kernels, because for those we suddenly have the problem of barriers and other collective operations between work items. And this could be solved by just spawning operating system threads, maybe, but that's something that would be very inefficient and also hard to debug. We want to, in SimSYCL, we want to constrain ourselves to executing everything on a single thread because it's the most debugger friendly. And so what we do is we use stackful coroutines or fibers in order to switch between threads whenever we arrive at a barrier. So if you take a look at the code on the left, you can see that we have an ND range parallel for kernel, and we perform some operations in every thread. Then we have a group barrier, some more operations, a barrier again, and then we exit the kernel. And now what the SimSYCL does to execute this is it enters this kernel for the first work item, and then once it arrives at the group barrier, it suspends this fiber. So this means it saves the current stack and local variables and switches to the next work item and starts the same function over for the next work item. And when arriving at the barrier again, switches to the next work item and so on until all work items of the group have been started and all have arrived at the barrier. And then it starts over again and resumes the first work item for the barrier. And this is something that can't just be expressed in a normal C++. It needs something called stackful coroutines because, well, we need to keep the stack and all local variables intact for every work item. And so what we use is boost context, which allows us to do stackful context switching. And this has the advantage that, well, first, everything's in a single thread, so we can easily step through a kernel with a normal debugger. And it also allows us to detect if the user invokes the kernel functions, collective functions in the right manner, and if all work items eventually arrive at the same collective operation, group operation. Yeah, so what we do in general to help a user verify that their program is a correct SYCL program is that we try to be as strict as possible in adhering to the SYCL specification. So that not only means implementing everything. I mean, we have not implemented everything yet, but we're getting there. It also means that we do not implement extra functionality. So a lot of the production grade SYCL implementations have additional member functions. For example, on some SYCL classes, an example is the property list, for example, which doesn't have any member functions at all in the spec, but you can typically still call like get property on those. And these are things that are not in standard. So if you're an application developer, you want to know that whatever you're writing there is actually not a conformant SYCL code. And you want to be able to identify this subset that's actually supposed to be compatible with every production grade SYCL implementation out there. And another thing that we can do, since we're not focused on performance, is that we can perform a lot of runtime checks within our SYCL API. So one would be, well, recognizing whether users use group operations correctly. Another one would be to verify that that we don't exceed the device memory capacity, or that we don't exceed we don't exceed the maximum workgroup sizes that the device supports, and so on. And one thing we can also do, since we don't use actual accelerator hardware, is that we can just build every SYCL program with address sanitizer, for example, or run it through Valgrind. And this just allows us to use the debugging and verification tools that everybody loves in their SYCL programs without special support from the vendors of any backend API that the user might choose to use. So to go a bit deeper into the runtime verification that we're doing in kernel code, this is an example of an incorrect SYCL program when it comes to group operations. So as you can see, there's ND range kernels being launched, and then the kernel performs a group operation on the work group, but only for a single work item. So only a single work item participates in the barrier, and all the other work items exit the kernel immediately. So this is illegal SYCL code, and depending on what hardware you're running this on, it will either just silently pass, or it will crash, or it will hang. I don't know. And what we can do in SimSYCL, and what we do in SimSYCL, is that we detect this condition. So for every work item in an ND range kernel, where we do this, where we keep separate execution stacks alive, we actually check if all work items arrive at all the group operations in the same order, and actually arrive at the same group operations. So running this program with SimSYCL gives you the error message that you can see below, where it will exactly tell you what kernel executed which group operation, and why it failed, and and ideally also what the user should be doing instead. Another thing, this is now more on the implementation side of things. We're also using C++20 as the implementation C++ standard. We kind of expect SYCL to move on to C++20 or a higher standard in the near future with SYCL Next. So we actually implement the SYCL interfaces using concepts. That's something that's very helpful, because a lot of the pros of the SYCL spec actually uses C++ concept-like language in order to define what the types parameters and template parameters have to be. And yeah, this also gives us a more strict checking of the API requirements, so that, again, a user that writes their program against SimSYCL can be more confident that their program is actually going to work with other SYCL implementations as well. And yeah, since we have this higher standards requirement, we require rather recent compilers, but we actually can allow different compilers, not just Clang, or not just Clang derivatives. We can actually build SYCL programs with GCC and MSVC as well, because, well, at the end of the day, it's just a library-only SYCL implementation, no compiler plugin, and no other fancy compiler dependent or implementation dependent functionality that we're using. Now, on the user-facing side, one of the most interesting features of SimSYCL is the inversion of device capabilities. So typically in a SYCL program, you would query through SYCL get devices, for example, what devices the system has, and then depending on the devices present, you would select different kernels, for example, or you would decide how to distribute the work in your program. But for SimSYCL, you do it the other way around. You tell SimSYCL what kind of GPUs you want to see, or you want to see emulated or simulated on your system. And it will then, when you enumerate devices, give you exactly that. So if you write a program that is supposed to adapt to different to different GPU vendors or to different numbers of GPUs on your system. You simply test it by giving it different system specifications. You can do this either programmatically through a SimSYCL API or by giving it a JSON file that basically just enumerates all the SYCL info device members and properties. And another thing that we would like SimSYCL to become is kind of an executable specification of SYCL. So since we do not need to focus on performance, our code base becomes radically simplified compared to a production grade SYCL implementation. So, for example, a lot of the functions in SimSYCL just become empty functions, like SYCL event wait. It does nothing because everything's executed in order. There's no DAG that needs to be considered and so on. So a largest part of SimSYCL is actually just the header files that declare functions, and the implementation is actually very minimal. So SimSYCL can become a testing ground for new SYCL user-facing APIs to see first, are they easily implementable? So it's easy to play with, and also are they implementable in a library-only implementation and on the host? Because these are both the things that we consider to be valuable. That SYCL programs should be able to compile without special compiler support, and also should be able to run on a host-only implementation, just so that we can support this very frequent testing and CI use case. So there is like most of the features of SYCL we can support with this SimSYCL model, except for the tool that I mentioned before, like these asynchronous communication and waiting on host access issue. And another thing that's currently in the spec is the kernel attributes, the C++ attributes. These can't possibly be supported without a compiler plugin or without a dedicated compiler. So we don't have them. And also there's queries on kernel properties. You can query whether a kernel is can execute on any device in the system. Things like this are not possible with SimSYCL because it would require us to inspect the properties of the kernel lambda in some way, or actually compile it to some sort of device code in order to figure out its properties and to see if it can run on the device. So that's obviously not possible to do. Another thing that's not on the list right now is also if you allocate USM memory in SimSYCL, it will tell you when you go out of memory. For buffers, it can't, because buffers have these buffers are not tied to devices, so they need to be able to be moved around. So this is also not very clear how to report an out of memory condition for this, for example. So now to show you some evaluation results of what we're doing. One of the central things that we're focusing on in SimSYCL development is to speed up the edit, compile, debug cycle in order to ensure that a user arrives at a running program quickly and doesn't have to wait on the compiler for ages. So what we're doing is we have two SYCL applications that we compiled with versions from SimSYCL, Adaptive CPP, and DPC++ from around January. And as you can see with our system, it's with our system, you can see that SimSYCL is typically much quicker to compile both SYCL Bench and Celerity, where SYCL Bench is an application that has a lot more kernels and it's a lot more SYCL focused, where Celerity has a lot of code that does not touch SYCL, has a lot of other functionality that's not related to launching kernels or performing SYCL operations. And especially for debug builds, Celerity is much faster than production grade SYCL implementations. And this is actually also the metric that we consider the most important because, well, after all, you're trying to get your program to work, you're trying to debug, you want to have a fast debug build. Now, just to show some performance benchmarks, I mean, like I said, performance is not a priority, but still you want to be able to execute your SYCL program with a small problem size. We still want it to complete eventually in order to see whether the results that you get make any sense or not. So this is for a very simple benchmark. We do the vector addition double precision benchmark from SYCL and we run it with SimSYCL, adaptive CPP, with the library-only implementation and with the library-only implementation constrained to a single thread, and also with DPC++ and the OpenCL CPU backend. And as you can see, the performance or the latency execution time of this vector addition is rather good for a small number of vector elements. Of course, it gets slower as the number of elements increase, and only at a rather large number of elements do both DPC++ and adaptive CPP exceed the performance of SimSYCL here, because, well, they're multi-threaded, obviously, and they can make use of other optimization techniques that SimSYCL can't. But SimSYCL is fast for very small examples here, because it has much less bookkeeping to do for submission, because it's simply, when you do a parallel for, it just immediately starts running a loop on the host, so less latency there. This, of course, like when you look at more complex benchmarks that involve ND-range kernels, this picture is probably going to look a bit different, but we still want to make sure that simple problems can be run with SimSYCL, so that you can make sure that your program produces some sort of meaningful output. Another metric is, well, let's regard this more as a metric of progress in our own implementation. We run the SYCL CTS with SimSYCL. Now, these are results without the large and slow full conformance checks. But SimSYCL now manages to pass more than half of the SYCL CTS, where DPC++ is almost past all of them in our run, again, with the CPU backend. Adaptive CPP, not so much, although adaptive CPP, as far as I know, doesn't really focus on getting the CTS to pass. We can say that SimSYCL is on a good way to becoming a more or less fully conformant implementation, with the caveats that I already mentioned. And yeah, so that's SimSYCL for you. Try it out, give it GitHub stars, and take a sticker. I have a couple of stickers left. I'm gonna place them outside afterwards. So thank you.